Cool. Not too many headaches for today. Only thing that I noticed is that I can't get into Husky CT right now. We already know what we're doing, so we'll let UConn figure out how to get us back into our learning management system, and we'll just focus on learning. That'll be our plan. We'll let someone else manage the manage system. But we're back. How did weekend go? Did you actually get a chance to like regroup, ready for the semester? No? Working? On schoolwork or? Alright. Nice. No rest for the wicked. Yeah. We had Monday off. Nice time to reflect and think about, like, remember on Friday when we were talking about free body diagrams? I can't wait to get back to that. And I had so many questions that I didn't get a chance to ask on Friday. So now that we're back, I can finally ask that question. What was it? Yeah. So I think this is homework 1. Like this one where it's saying like solve for x of t. Oh wait, where's the? There was a picture on there, right? Or no? There it is. All right. I'm like, what? Okay. All right. So the picture's there. So when I'm saying like solve for x of t, then there should be like plug in any value of time, and there should be some number for it. And there, if you want, we can jump right into this question for today, or kind of like plug along the same process that we have been going. Did anyone else get up to this part and they had questions, or do we want a quick review on where this is coming from? Yeah. Okay, so the question that came up was like in this part 2. So as we get out of the textbook problems, this is the next part where it's saying solve for x of t for 3 different cases. One where a block is sliding on a rough surface, so there's some kind of friction. One where a block is sliding, but there's a damper opposing that motion. So the faster it moves, the bigger the force to slow it down. And then the last one's a spring that the more it moves away, the more the spring wants to pull it back to the wall. And that, so for these 3 cases, yeah, we could jump off right here. Then we'll come back to what we were working on last time. Yeah, let's just make a whole new thing here. So general process is kind of like, first you have to find the differential equations. Like how is x related to velocity? How is velocity related to acceleration? So finding those governing equations first. And then if we want x of t, the solution, then we're going to integrate the acceleration equation twice to get to the point of like, now I know what x of t is. So in order to get there, where do you think we should start? What do you think would be, based on just a hunch of what we did all day Friday? I know it's been a long time since then, basically like a year ago. Draw a free body diagram. You got to identify what forces are actually changing motion. Because F equals ma, so if I can identify all the F's, then I know VA. Like there's only going to be one A term, and then I can go from there. So I need free body diagram A, free body diagram B, free body diagram C. So what are the forces in these three different cases? And I just drew a point because I only care, I don't care about like rotation of the block, or if I do, then it's not rotating, so I can say that there's no rotation, but a point mass, what forces, and where are they pointing? And from there, then we can get diffy Qs and start going from there. I don't know if this is like way more information than you asked for x and t, but the quick answer was like some function. X of t is 2 times t squared over 2. Yeah. Oh no, I'm just like is that a force or is that oh yeah. It is a force? Okay. Like position, it's a force that is position. This one is giving you like a reference frame that like in this state x equals 0. So when x equals 0, it's right there. And as it moves forward, x is no longer 0, it's something bigger. That's what that one's saying. That it helps to have like a coordinate frame reference of like what is a positive displacement versus a negative. Initially, so we do have some initial conditions if you're so inclined. That x at t equals 0 equals 0 meters, and v at t equals 0 is 10 meter per second. So we know initially sitting somewhere, but it's not sitting still. It has some initial velocity. Yeah. Yeah, B is called a damper. Do you know what a damper is? Like for a door. What? Like for a door closing. Yeah, door closing. Those use dampers. So a damper. Here, let's look it up because I can draw it, but it's not going to look good. this one. This one's not bad, like a cross section kind of drawing. Oh. The like general idea is that I fill up a cylinder full of oil. It could be anything. Like I could use water, oil, air. Like it could be an air damper. And then there's something that's going to move through the oil. The more holes I put in it and the bigger area that the oil can pass through, the less damping it has. The more I constrict the fluid to go through that kind of orifice that's in there. Engineers love like phallic terms like orifices and like, you know, like vibrating things. But so the more I restrict it, the more damping I get. And because it's a fluid flowing through a hole, it's mostly linear. We can approximate it as the faster I move the damper, the more force the damper gives. If that makes sense. And usually like a car, a mountain bike, a door, there's a spring and a damper both attached to the same spot, so that as you open the thing, the spring pulls it back and the damper slows it down. So here we're splitting them up into two different diagrams because it's usually easier to solve for one at a time. And then it's just a simple convolution to put them all together. It's not super simple, but that is the fancy way of saying solve at the same time, the convolution of the two functions. For A, I got 10 minus 12.9. 10 meters per second and minus 1/2. What was it? Is that G times mu times 1/2? It should be like around 2, right? Shouldn't it be? Yeah, 0.5 times 0.5, right? So it should be like 1/4 G. At least that's what I was thinking. All right, so I did see as I was kind of walking around and just like stealing your work and displaying it for everybody. Mg, 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 some kind of normal force, normal force, normal force. Is there any acceleration up or down? What is a up? Nothing, right? Whatever n is, or whatever mg is, the floor is always applying n normal to it. So that makes our life a little easier because it's just going to move left or right. Then I saw 2 forces. What was that like forward force? What did you mean by that? Did anyone have like something pushing forward on A? Yeah.
So there's just like initial velocity, so I'm trying for that.
Okay. Is velocity, can I say that velocity is a force?
We need to cause velocity of the force.
Okay.
It's already there. I guess not.
Yeah, okay. And did you have, I saw you shaking your head.
Oh, I was just going to say, like, the velocity term, like, once you integrate the sum of force equation, like, log in sum of force.
Yeah, so kind of thinking to the next step of like, once I have a differential equation, as I integrate it, I'm gonna use that initial velocity as part of that integration process. So that's one way to like think about like the math part of it. And then as a gut check, always think about like, if I'm drawing this like forward thing, trying to account for like, well, I know it's moving. I want something to say that it's moving forward, but velocity itself, it's not units of like kilogram meter per second squared. So maybe multiply by mv. but that's still a kilogram meter per second. So now it's momentum, but not like a change in momentum. So in terms of like, if you're given if we have initial conditions, like we know where it's starting, it's not telling us the forces that are acting on it during the motion. It's just giving us like that initial starting point. So we can't, yeah. In terms of like, oh, there we go. So I can't draw anything forward. At least I didn't hear anything that we could draw forward. But what was pushing backwards? What's that one? Friction. Force of friction. All right. What about for the damper? This one. Yeah, some kind of like force of the damper, something like that. Then we'll figure out what to do with that when the time comes. What about for the spring? This one I definitely saw both this way and this way. Is the spring always pulling to the left? No. Yeah.
In this case scenario, wouldn't it be pulling to the left, or I would assume most of it is the time frame?
Okay, so maybe assume that it's pointing to the left, and maybe we could be wrong, right? Like, and that's kind of one of the things we do in statics, right? Like, we draw the free body diagram of the bridge, and we assume that the reaction force is pointing up, just because. And if it ends up being negative, then we flip the vector, turn it the other way. Yeah, so we could just make an assumption that it's pointing one way, and then go from there. Any other thoughts on spring force? This is one approach. This is my approach, and if you like it, steal it, use it. And a lot of other people do this as well, but this is the way that I like to think about this kind of problem, is that when I'm drawing a spring force, I think about if I have a positive x displacement. So when x is positive, is my force positive or is it negative? Which direction would it face? So here, when x is 0, there's no spring force. The spring is not applying any tension. But when I pull it to the right, what happens? Is it pulling it further to the right? It's pulling it back to the left, like a restoring. It's called a restoring force. So the more you take it away from whatever it thinks equilibrium, whatever equilibrium has to be, the more I pull it away, the bigger the negative force is. So that's the way that I like to think about this problem. And that way I'm always I'm always thinking about positive displacement and then where the force ends up for that positive displacement. So even if the spring was on the opposite side, it would still be the same case, right? For a positive x displacement, I still have a negative spring force, even though I put the spring on the opposite side. Kind of makes sense. This is the way that I like to think about it. There's more than one way to get to the same answer. But that way, I always end up with restoring spring forces. I don't end up with... It would be nice if I had like an infinite velocity producer spring, that the more I pulled the spring, the faster I would accelerate away from the spring. But I don't have anything like that. I don't have any technology that does that. I think you need some kind of like time-space warping sort of thing for that to happen. Well, there are unstable systems. I shouldn't say that. Like an upside-down pendulum does have that case, where the bigger the angle, the more it wants to move away from where it started. But it's not forever. It doesn't do that forever. Cool. All right, so now I've got A, B, and C forces that are acting, and the only forces that are causing changes in momentum are those forces pointing to the left: friction, drag, friction, damping, and spring force. So in part A, what does MA equal? Yeah. Force of friction. And to the left. So which way is MA pointing? Also to the left? Yeah. Yeah. Okay, so you're saying that
slowing down.
So you're creating like a reference frame where left is positive? Is that what you're thinking?
No.
No, you want left is negative? It is. It's a little confusing. So again, this is my system. It works for me like 99 out of 100 times. But once I say right is positive, then anything pointing left is negative. So in this case, MA equals negative FF. That way, that positive initial velocity is losing speed because it has that negative acceleration. Again, if you want to rewrite time and space and create your own coordinate system, you're welcome to, but you're going to have to like keep track of the books as you're doing that. All right, so this equals that. So MA equals negative force of friction. And what is force of friction? We have numbers for it, but like, what's the formula for regular Coulomb friction?
Mu times the normal force.
Mu times normal force, and what's normal force? Mg. Yeah, mu. So N is W. W is mg. So A equals negative mu g. Cool. Do we have x of t for part A? Do I know what this thing is doing for all time? Yeah? Why do you say yeah?
It gives us mu, right?
Yep. Yeah, we have mu. It's just, and mu is always like some kind of constant. I mean,
and we know gravity.
And we know gravity hits here on Earth. Yeah.
Yes, so then we know it.
And we're not in a boat traveling like east or west. We're kind of like, because there's the Yotvos effect that if you're traveling east or west, gravity changes by like 1 millimeter per second squared. But yeah, gravity's some constant. Yeah.
Okay, so it's constantly.
Okay. So constantly slowing down. Good. What does that look like for our x of t? So I have A. A is constant. So what is x of t? This one I know I'm asking you to like stretch back into like high school and freshman year. Pull out information. What do you think? Did you plug it right into Yeah. Okay. Yeah. And then, yeah, and then velocity stuff. Oh, I see. What is x? How far is it going to move? I guess that's one question you could ask. We know x of t, but we know how far t moves. Okay, what are those equations? They exist, right? Yeah. Okay. You remember their names or anything? Kinematic? Yeah. Okay. Yeah. You can always look them up, right? Okay. And that we're kind of coming around to like kinematic equations. Or you can integrate, yeah. And yeah, I should add a. So if I know like initial position, I know its initial x position, I know its initial x velocity, and I know the acceleration is constant, then I can say plug in those values and I get like a solution, right? So now I know x of t is 0 plus 10t minus mu g t squared over 2. So does that ring a bell? Like, yes, these things. So these are called kinematic equations because if you can create a free body diagram that has a constant acceleration, then the geometry of its motion is always the same. It always has the same kinematic end result for that, for constant acceleration. We have to remember that. A is not always constant, but it can be. Cool. And in terms of like solve for x of t, this is what it was asking. Like, can you get to this step of like, we know what a is, so now x of t is this. What about for part B? What is MA? So it's negative ft. So whatever that force of the damper is, we identified that that's what's causing motion. MA is negative fd. For a damper, for linear dampers, which we can assume here, you can make nonlinear dampers, and there's all sorts of like cool engineering that goes into like changing how the damper works depending on the speed. My mountain bike has a cool like nonlinear damper in it, so that high speed has a little bit less damping and lower speed has a little more damping, so that as you're pedaling, it doesn't damp as much or damps more. But anyway, so MA equals negative. I'm gonna call it like B because that's like, oh, we're coming in here. Like this B is 1 kilogram per second. So B times V is our like damping force. And that's the linear, and that makes it like a linear damper. So the faster I move, the bigger the force. If I'm not moving at all, no force, which makes sense. The damper shouldn't be like opposing motion when there is no motion. What? Cool. So now just plug it right into kinematic equations, call it a day. No? There's a V in the term, right? Yeah. So A is no longer a constant. A changes with time because V is changing with time. So what do we do with that one? Integrate it? Okay. Yeah, derivative. How would derivative and integration help? What would you do? Take a derivative of function or integral of A with respect to V. So what it, and this is what I was like trying to figure out, because we do need a derivative definition, and then we do need to integrate it. So we need both of those things. What is the definition of A? Distance, sorry, derivative of V. Yeah, so they're all connected, right? Like A is dV dt, V is dx dt, and this is d dt of dx dt. So like d squared x dt. So I end up with like dv dt equals negative b over m v, like that. I'll let you try that one for a second. See where you're at. And B, so, and again, like B and M are just like constants, so we don't have to worry about like solving for those. We're just trying to get, at this point, just trying to get B as a function of time or something. Have you seen this before? Yeah. Okay. Oh, with this one? Like dv dt? I think so. I'm not completely sure what it is. Something. Yeah. This kind of differential equation. Yep. Okay. Okay. Yeah. Okay. Yeah. Okay. Yeah. So at this point, like we should be able to. Now it's like a math problem. Yeah. Like we identified all the forces. We use engineering intuition. So at this point, we have gotten to math our way. Yeah. this kind of problem? Does it look familiar? Okay. This class is hard because you have to like take lots of different classes and pull them all into one spot. It's hard to remember like where they're coming from. Let's just do like a refresher note. So if you had like this kind of function, dy dt is negative y. Do you remember? Does this look familiar, or did you use different f? I don't know. I didn't take calculus like here at UConn within the last couple of years, so all of my notation is from Ryan Cooper when he was 19, 20, 19 or 20, not the 1920s. But I'm not a vampire, at least that I'll admit on YouTube. Can I do this? Dy over y is negative dt. Yeah? No, nothing. I didn't do anything like weird, right? I mean, it might seem weird, but all those dt's and dy's, they're just algebra. Like they're just different functions. It is connected to y, but it's an independent variable from y. And once I have dy over y, really this is the integral of 1 over y dy equals the integral of negative 1 dt. And because we have like bounds on like what conditions we care about, we can start at y0 and go to y, start at time 0 and go to t. So that it's always exact integrals, and I don't have to worry about like adding that because integrations are always like it's this solution plus a constant. But if it's an exact integral, you don't have to worry about that constant. Just throw it out because you're subtracting the same constant from itself. So log of y minus log of y0 equals negative t. Log minus log, again, this one's kind of like fancy high school algebra tricks. I'm a math magician. You can take a difference and turn it into a fraction with logs. If they're added, then you can turn them into like y times y. If they're subtracted, then it's y over y. So y becomes e to the negative t times y0. That one's like our refresher note. Can we do same thing here? Same process? All right. Yeah, so now we have like v of t. All right. Okay. So as I was doing that, some people were getting to the solution, right? Yeah, so now we've got like velocity as a function of time, but how far did it move was the original question. So I can plug in again, dx dt is b0 e to the negative, oh my god. It's a bad x and d. And do the same kind of process, right? Integral from x0 to x of dx equals integral from 0 to t b0 e to the negative b over m t dt, where I took like that dx dt, multiplied the dt by both sides. Now I've got x of t is some kind of e to the negative b over m t function. Like, go up a little. Might help. Yeah. Where did that b0 come from? Yep. So the way I like to do it is turn this into an exact integral. So it starts at b0, ends at starts at 0, ends at t. So otherwise you have to say log b plus c. This is b over m t plus c plus like b, two extra constants. Then you have to go and solve for those based on b0. So I like this step in general, especially when you're dealing with dynamics, which are almost always they're a general class of problems called initial value problems. You know the initial values, and you want to solve for what happens later in time. So I know it has some initial momentum, some initial position. Let me figure out what happens, whatever, 30 seconds later. So I like to use these bounds. Otherwise, this step, if I try to do integral 1 over y dy equals integral negative 1 dt, the solution is log of y plus c equals negative t plus like d. And I could add those two together, like get rid of one of them or something, but say like log of y plus c. Now I need to solve for c based on the initial condition that when t is 0, log of y, or sorry, that y, when t is 0, y is y0. So that's why I like to just plug it in directly, since I already know I want to go from 0 to t and y0 to y something, or v0 to v. What'd you get for x of t? Where did that one end up? Yeah, v0 is 10. Yeah, so you have initial t, but x0 is 0. So the left side where we're integrating dx, and we just end up with like x minus x0. So it's x of t, because x0 is 0. Right side we have the integral that e to the negative b over m t is negative m over b times e to the negative b over m times t. That one usually derivatives and integrals get flip-flopped. At least if you're not like doing derivatives and integrals every day, which you're missing out if you're not, but c'est la vie. When I evaluate at t, then I have that v0 m over b e to the negative. So I have this equals negative v0 m over b e to the negative b over m times t. What about the at 0? So minus when t equals 0. Is it 0? No? Yeah, e to the 0 is 1. And that's usually the tricky step that So negative V0M over B times 1. So we end up with it, and it kind of makes sense that if velocity is like some kind of exponential decay function, position should also be an exponential decay function. But it's not going to be a final 0 position. It's going to be some final non-zero position. And that's what this term is telling you. That whatever your initial velocity was times your kind of non-dimensional damping. Well, I mean it's dimensional, but damping per mass. That's how far you'll end up for that damper. At least eventually, at t equals infinity. Oh.
And to that, you add the initial position as well, the x0.
Yeah, and I would like add an x0, but here x0 is saying that it starts at 0. Yeah, but we could add that x0 as like the general. This covers every damped forward motion.
V0 is 10.
And then V0 is 10. Yeah, start off at 10 meters per second. Cool. All right, mic drop. Thanks a lot. We'll be back Friday and pick up where we left off. Thanks.